Welcome to Watershed. My name is Watershed 2.
And I'm Nick.
And I'm Alex.
And I'm here to lead you through your watershed journey. So let me break it down for you. Our watershed is home to numerous variables that are actively affecting each other. The ones we test for are pH, ammonium, dissolved oxygen, turbidity, conductivity, salinity, nitrates, temp, and flow rate.
pH refers to how acidic or basic liquid is. It is known as the potential of hydrogen. Acidic solutions are measured to have lower pH values than basic or alkaline solutions, which have higher ones. A good pH range is generally a little alkaline, which is usually between 6.5 and 8. Having water that's too basic or acidic can harm the animals that live there and ultimately affect plant life and nutrient management.
All right, passing it over to Holler now. Ammonium is a positively charged ion, which with the chemical formula NH4+. It's essentially ammonium with a little extra proton, hydrogen, ion added. It comes from a pungent gas that is then released and decomposed into the water. 0.3 and 0.6 ppm is an accepted range for ammonium. At high concentrations, it can become a pollutant to the stream, hurting the life within it. The water changes through nitrification and nitrifying bacteria.
Dissolved oxygen refers to the amount of oxygen gas that is dissolved in water, which is crucial for aquatic life. It is essential for fish and other aquatic organisms to breathe and survive. Healthy dissolved oxygen levels are around 6 milligrams per liter and up, although it rarely exceeds 10. While DO is under 5 milligrams per liter, ecosystems become at risk of stress to aquatic life due to a lack of oxygen that the organisms need.
Now, turbidity is the cloudiness or haziness of a fluid caused by large numbers of individual particles that are generally invisible to the naked eye. A good range for turbidity is usually below 1 NTU. This matters to watershed because turbid water can affect cleanliness and the animal's habits, which keep the water and plants healthy. More turbidity means there is murkier water, and this means that sediment is being carried along with other elements and chemicals, and this can make breathing even more difficult for aquatic organisms.
Conductivity in water is used to account for the amount of potential electricity that is able to be conducted. It affects how energy can be transferred within the water. 150 and 500 is an accepted range for a common watershed. Comes from the presence of dissolved ions in the water. It matters to the watershed because if the readings become too high, it can be a key indicator of the water quality. The conductivity is often caused by the dissolving of ions such as chlorides, nitrates, and sulfur ions, and correlates to things such as higher salinity.
Salinity is the amount of dissolved salts present in the water. Rivers typically have low salinity levels with a salinity of less than 0.5 parts per thousand. This means that there's very little salt compared to seawater, which has an average salinity of about 35 parts per thousand. Salinity matters because high salinity can make water unsafe for drinking and for wildlife.
Nitrate is a naturally occurring compound formed from nitrogen and oxygen atoms. It occurs naturally in all surface water and groundwater as well, although higher concentrations tend to happen where fertilizers are used on the land. Nitrates are produced during the natural decay of plant matter in soil, and a good nitrate reading for freshwater is generally considered to be below 40 ppm, which are parts per million. For freshwater aquariums and below, the recommended amount is 10 ppm for this freshwater.
Temperature is defining how much heat the water holds. A good range is between 5 and 25 degrees Celsius. The reason this matters to the watershed is because too high or too low of a range can kill living life. And at a high temp, more algae and bacteria begin to grow, which can become more dangerous.
Flow rate is the speed of water passing a specific point in the river, measured in meters per second. It matters because it significantly impacts water quality, habitat conditions, and aquatic life. Excessive flow rate can cause erosion and flooding, while low flow rate can reduce oxygen levels, which is harmful. Flow rate in our watershed can range between 0 and 3 meters per second. 0 meters per second is stagnant water, and 3 meters per second is a raging river.
As you advance in your watershed journey, you'll need to become a master at collecting data.
Time is limited on data collection days, and it is your responsibility to make the most of your time. Many probes require calibration, so make sure you account for that beforehand. It is always best to come equipped with a plan upon arriving to the river. It is helpful to plan out each role accordingly. For example, Person A might be responsible for setting up a turbidity probe ahead of time because it requires a 5-minute warm-up. Meanwhile, Person B may be responsible for putting flags in the ground. Everyone should be assigned to their variables ahead of time, so no time is wasted figuring this out at the testing site.
We have made some changes since the field guide was written. The previous Watershed class followed a river chart with 21 possible testing locations per water stream, where 12 of those spots were randomly selected to test. This year, we used 30 possible spots and tested 12 of those, which allowed for more random locations to be tested. The nitrate sampling is vastly more efficient than in previous years due to the new vernier probe. Here's how to calibrate and use the new probe. These directions are the same for nitrates and ammonium. So 30 minutes before use, the probes must be soaked in 100 ppm solution in the short-term soaking bottle. When you are ready to calibrate, choose 2-point calibration on the LabQuest and let the value on the LabQuest settle before entering 100. Then click Save. Remove the probe from the short-term storage bottle, pour the solution into the 100 ppm bottle, and rinse the probe with distilled water. Submerge the probe in the 1 ppm solution and let the value settle, and then click Save. Remove the probe and rinse again. After this, you may test. It should then be stored in a long-term storage container after you are finished, which has a sponge in the bottom.
The places we tested in 2025 consisted of different branches of the Conestoga, including Mill Creek at Kurtz Mill, the Conestoga River at County Park and Millcross Road, Lidditz Run at Millport Conservancy, and Big Spring Run in Lampeter. We also tested Peckwood Creek and Silvermine Run, Sickman's Rail, and Climbers Run at the Nature Center.
Through extensive data analysis with the use of Data Classroom, we were able to make several inferences about the variables that affect our watershed, hence the health of our watershed. For example, a p-value of less than 0.01 for the comparison of nitrates between two of our rivers, the Conestoga and the Pequea, shows that the Conestoga has a significantly higher amount of nitrates with an average of 4.48 parts per million compared to 2.19 parts per million. The p-value of less than 0.01 means that the null hypothesis is rejected and the alternative hypothesis is accepted. The amount of nitrates is significantly different between the locations, and from this we were able to infer that the Conestoga River likely has greater nutrient pollution and dissolved ions, possibly from agricultural runoff or urban wastewater, leading to poorer water quality in comparison. The data suggests that while both rivers share similar turbidity, the Conestoga River is more impacted by chemical pollutants. This comparison of pH between the same two rivers indicates that the Pequea has a higher pH, but in this scenario, the difference isn't quite as visually apparent. But still, the p-value of 0.02 suggests a significant difference. The average pH in the Conestoga is 8.2, while in the Pequea it's 8.4.
The data depicted is a representation of how much one variable can vary even in one watershed. The example we chose to magnify was temperature. When looking at the data, it is important to note that the variation in temperature was likely due to a few different factors, such as shade coverage, location, and recent amounts of rainfall, along with the general temperature just being lower. Days that were colder and after recent rainfall were rivers such as Climbers Run, Big Spring Run, and Millport Conservancy, showing that the temperature is highly reliant on the weather. It is also an important note that statistically, the two main rivers remain similar, but there do appear to be some cold spots within our watershed.
Now that you have learned about the basics of Watershed, it is important to begin preparing for what lies ahead in this mod. There are some questions to keep in mind that will help you understand the main focus of this course. Firstly, how does the cleanliness of water affect benthic life? More analysis of benthic is needed to come up with a confident and definitive conclusion of the direct effects of the variables on benthic life. Secondly, how can collecting data help us further our understandings of our local watershed? When it comes to collecting data, more is always better. One of the important decisions is where to collect the data. We suggest you revisit some spots and possibly find some new ones. such as spots on the Little Conestoga or even on the Susquehanna River itself. It would be intriguing to observe the differences between the three distinct sizes of rivers, all the tributaries of the watershed too.
Questions like these will help keep your research and data focused towards the direction of Vamad's big question, which is, how do the rivers of our watershed differ from each other? With that, we hope you learned a lot today. Your watershed journey will be one of great knowledge, perseverance, problem solving, and most importantly, fun.